On behalf of my co-authors, the scientists in charge of the U.S. Volcano Observatories in Hawaii, California, the Cascades, Yellowstone, and Alaska, this is Tina Neal of the U.S. Geological Survey's Volcano Science Center. This talk will briefly examine highlights of U.S. Volcano Observatory progress over the past decade and offer some collective thoughts about the next 10 years. To begin with, let me remind everyone that our 5 U.S. volcano observatories, operated by USGS and our academic and interagency partners, have 3 broad and interconnected goals: to monitor volcanoes and detect signs of unrest, to assess volcano hazards and communicate helpful information to support public safety, and to conduct fundamental research into volcanic histories and processes. An AGU session in 2010 addressed the same retrospective and forward look. So let's review a few of the forecasts that were largely correct. Most obviously, many new monitoring tools have indeed come to pass, some developed by USGS and others by university and government colleagues, both domestic and international. Examples would include infrasound to detect explosions, expanded constellations of radar satellites to detect deformation over broad volcanic areas, high-resolution cameras, unoccupied aerial systems, and miniaturized sensors of all types. Alarms for volcano monitoring information were expected to improve, and indeed, computer and data science-driven alarming of data streams from infrasound and satellite imagery, for example, have increased our 24/7 vigilance. In the realm of communication technology, changes have revolutionized our ability to integrate new sensors quickly into real-time networks, communicate with each other in new and increasingly mobile ways, and ensure more data are available to the broader science community and the public more quickly. Many new volcanic process models, some elegantly physics-based, now routinely assist observatories in characterizing the state of volcanic systems and helping to produce forecasts. And more observatory staff are using event trees to constrain unrest and eruption scenarios, contributing to improved hazard assessments, forecasts, and public hazard messages. Application of observatory knowledge to partners in emergency management, as forecast 10 years ago, have received a great deal of attention in the last decade. Sustained efforts in interagency response planning, the founding of the California Volcano Observatory in 2012, application of insights from social science to observatory communication practices, and the development of standards and protocols for operations, all achievements represent significant progress. As anticipated, international collaboration at all levels of observatory science and operations has grown over the past decade to the great benefit of all. So some of the catalysts for progress in the last decade include the emergence of cheaper, smaller sensors, proliferation of the new satellite platforms with high-resolution imaging sensors across the electromagnetic spectrum, big eruptions in Alaska and Hawaii, for example, at Okmok, Bogoslof, and Kīlauea. Each eruption was a proving ground for new tools and new ways of doing our work. And finally, important funding bumps certainly helped fuel progress, initially from the American Recovery and Reinvestment Act, then momentum and push for the National Volcano Early Warning System, and more recently line items for analog to digital conversion at sites in Alaska and a Lahar warning system at Rainier. Turning to the future, there are many recent guiding documents to guide favored directions for progress over the next decade. Here is just a partial list, and across these strategic documents, some themes emerge. 1, our monitoring and science efforts should focus on the most hazardous volcanoes and those that can help us answer the most important volcano science questions. 2, partnerships are critical for progress and success of the Volcano Observatory mission. 3, standardization and interoperability across observatories should continue, and this will increase efficiency and offer more mutual support in volcanic crises. And finally, we must take care in adopting technology at a level that is sustainable into the future. So what will our observatories look like in 2030? Well, here are some thoughts. We'll continue to have the 4+ brick and mortar buildings with some new exciting facilities in Hawaii, but following broader trends in society, our work will become increasingly virtual and remote, taking advantage of new and improved mobile applications. Data storage, delivery, and backup will take greater advantage of the cloud, and monitoring instrumentation and data handling schemes will become more uniform across observatories. The National Volcano Early Warning System, or NVEWS, has an implementation plan that envisions a 24/7 watch office and data center. Some such entity will exist by 2030, but whether it is virtual or a distributed or actual facility remains to be seen. Scientists at observatories will have more and more familiarity with incident command practices and be ready to insert themselves quickly and seamlessly into the emergency response landscape. And observatories will have a greater emphasis on response planning internally. What are some of the new and improved services we would expect at our observatories? Fundamentally, our ability to forecast what will happen, when, how big, and for how long will be improved using better models, information from new and improved monitoring networks, and clearer understanding of each volcanic system in play. To get there, of course, we will need investments in basic research, instrumentation and data systems, and more geology and geophysics, both in the field and in the laboratory. Alarms will become multi-parametric, combining information from multiple data streams to intelligently alert duty scientists and others of changes in volcanic state with fewer false alarms. Another key future capacity will be the ability to produce dynamic hazard assessment products, responding to changing conditions and to help answer specific questions from stakeholders. Along with this are improved long-term hazard assessments using statistically sound probabilistic approaches and more helpful visualizations, a project already underway called Next-Gen Hazard Assessments. Continuing on this theme, observatories of the future will have caches of various portable sensor packages and nodal arrays, fleets of UAS or drones to tackle research questions as well as monitoring and response tasks. Cooperative deployments of UAS and nodal arrays, of course, will still occur, but these resources will become more standard observatory tools. Physics-based models will continue to improve and be used more and more as part of standard observatory operations to clarify the nature of activity and to help narrow possible outcomes of unrest and eruption. The next generation of satellites will produce a fire hose of data, and along with other emerging technology we don't even know about yet, observatories in 2030 will have systems to ingest huge data sets rapidly and add value for the analyst required to interpret them. Artificial intelligence and machine learning are the buzz right now, and it remains to be seen how much of a splash they will make, but clearly advanced computational techniques are critical to the future of data processing and analysis at volcano observatories. And finally, although observatories themselves will have advanced arsenals of instrumentation, cooperative projects with new partners to test emerging technologies, as AVO has done recently in the Aleutians with Lamont Doherty and the Moore Foundation, these efforts will continue. Who will be working at observatories in 2030? Barring big budget reductions, I suspect staffing across observatories should increase modestly, in large part because National Early Volcano Warning System as a program and authorized by Congress in 2019 will, if funded, require more people to design, install, maintain, interpret, and keep track of vastly expanded data streams at monitoring networks. Although as a group, we must continue to increase depth in computer science and information technology and data science among observatory staff, still field and laboratory skills and studies, boots on the ground geology, to continue to refine eruption histories and process studies, these remain very important. Staffing focused on facilitating community preparedness will also remain a priority. And finally, observatories will increasingly become diverse, looking more and more like the country that funds them. What would a big eruption or unrest look like in 2030? The scientist in charge at the Cascade Volcano Observatory, Seth Moran, sketched this first cut at a more functionally oriented, well-defined response structure based on incident command system principles. Such a plan is currently under consideration right now within the Volcano Observatory leadership in USGS and will, in some form, be the way of the future for large eruptions or unrest events. Our experience at Kīlauea in 2018 amply demonstrated the need for this. Please note the prominent role for external partners in the larger volcano community on this org chart, a relationship exercise during recent eruptions, and just this past week in the National Science Foundation's CONVERSE eruption tabletop event. How will such progress in the next decade be supported? Beyond base budgets of government agencies at all levels, which of course depend on the federal and state budget processes, and these remain uncertain. We will continue in the near term to benefit from current congressional supplemental funding to Alaska, Hawaii, and the Cascades. These funds are actively supporting important new research, new instrumentation, and hiring. If NVEWS were to attract new funding, this would be a source of new initiatives and growth, as well as a potential external grants program to offer increased opportunities for cooperative work. Such new funding, or the next big eruption, will offer opportunities for strategic investment rapidly, and collectively we need to be ready with priorities and ideas should funds appear. Of course, the most important resource is our people, the talented staff of the Volcano Science Center, allied USGS programs, and the larger volcano science community. To wrap up, let's contemplate a few known external forces or constraints that we face over the next 10 years. Clearly, societal exposure to volcano hazards is increasing, and the demand for volcano observatory services is as well. The current pandemic may forever change how we work, increasing the need for virtual workspaces, mobile applications, and data access. Funding uncertainty is always present at all levels, and we must take care not to overextend network maintenance commitments beyond what is sustainable without steady budget growth. Permitting of monitoring installations and other work, even in the name of public safety, especially in wilderness, can be and will continue to be challenging. To tackle this delicate interagency negotiation will take time and people. Finally, climate change colors just about everything we do. Integration and leveraging of efforts across scientific disciplines and government agencies must increasingly be the norm. In that vein, volcano observatories will focus on reducing our carbon footprint and consider how our far-flung monitoring networks can collect data of climate relevance. Thanks very much for listening. Please contact us with any questions or comments. We look forward to the discussion section at AGU.